Look up at the night sky. What do you see? Is it just a canvas of darkness, or is there more to it? Countless stars are scattered across the darkness, each one a beacon of light in the vast expanse. Each one is a sun, perhaps with planets of its own, orbiting in a delicate dance of gravity. But where did it all begin? How did these stars and planets come to be? How did this vast and intricate cosmos come to be, filled with galaxies, stars, and planets? The answer lies in an event of unimaginable power and grandeur, the Big Bang, a moment that changed everything. Imagine a time when there was no universe, no space, no time as we know it, just an infinite void. Then, about 13.8 billion years ago, everything we know exploded into existence from a single, incredibly dense point. This was the Big Bang, the birth of our universe. In a fraction of a second, the universe expanded from an infinitesimally small point to an incomprehensibly vast expanse, setting the stage for everything that would follow. The early universe was a chaotic and intensely hot place, filled with energy and potential. It was filled with a sea of elementary particles, the building blocks of matter, swirling and colliding in a cosmic dance. As the universe expanded and cooled, these particles began to come together, forming the first simple structures. They formed the first atoms, primarily hydrogen and helium, the lightest and most abundant elements in the universe, setting the stage for the formation of stars and galaxies. Over millions of years, gravity began to sculpt the universe, pulling together particles and shaping the vast expanse of space. The hydrogen and helium atoms, drawn together by their own gravitational pull, formed vast clouds of gas and dust, creating the building blocks of stars and galaxies. These clouds, called nebulae, were the birthplaces of stars and galaxies. Within these nebulae, regions of higher density began to collapse under their own gravity. About 4.6 billion years ago, in a spiral arm of our own Milky Way galaxy, one such nebula began to collapse under its own gravity, setting the stage for the formation of our solar system. As the cloud contracted, it started to spin faster and faster, like a figure skater pulling in their arms. This increase in rotation caused the cloud to flatten into a disk. The center of the cloud grew denser and hotter, eventually reaching temperatures high enough to ignite nuclear fusion. This process marked the beginning of a new star. This was the birth of our sun, a star that would become the heart of our solar system, providing light and warmth to the planets that would soon form around it. The sun's powerful gravity drew in most of the surrounding gas and dust, but some of it remained in a swirling disk around the newborn star. This disk was teeming with potential. This disk, called a protoplanetary disk, is where our Earth and the other planets in our solar system would eventually form. Over time, particles within the disk collided and stuck together, gradually building up into the planets we know today. Within the swirling chaos of the protoplanetary disk, dust grains collided and stuck together, forming larger and larger clumps. These tiny particles, driven by the forces of gravity and motion, began to coalesce, creating the seeds of future planets. These clumps, drawn together by gravity, continued to accrete material, growing into planetesimals, the building blocks of planets. Over millions of years, these planetesimals collided and merged, gradually forming larger bodies that would become the planets we know today. The early Earth was a hot and violent place. Its surface was dominated by intense volcanic activity, with molten rock flowing freely and reshaping the landscape continuously. Constant bombardment by planetesimals, along with the decay of radioactive elements within its interior, generated immense heat. This relentless energy input kept the young Earth in a molten state, preventing the formation of a solid crust for a long time. The Earth's surface was a molten ocean of magma, constantly churned by volcanic eruptions and asteroid impacts. These violent processes contributed to the mixing and differentiation of materials within the planet. Over time, a process called differentiation began to shape the Earth's structure. This process was driven by the varying densities of the materials that made up the early Earth. The denser materials, such as iron and nickel, sank towards the center, forming the Earth's core. This core would become the source of Earth's magnetic field, which protects the planet from harmful solar radiation. The lighter materials, such as silicon and oxygen, rose to the surface, forming the Earth's crust. This crust would eventually cool and solidify, creating a stable surface for future geological and biological processes. This process of differentiation is what gave Earth its layered structure, with a solid inner core, a liquid outer core, a mantle, and a crust. Each layer plays a crucial role in the dynamic processes that continue to shape our planet today.